starting from the coupled array of wires, which are not at all topological. Yes, I think it's on. Okay, so actually, I chose my topic for several reasons. First of all, one of my collaborators already gave a nice overview talk on a project on SU, topological phases in SU and cold atom systems. So I don't think it's a good idea to repeat almost the same thing once again. And also, this is more important, but actually, mechanism of generating topological quantum field theory in an array of coupled wire is at least formally quite similar to the similar mechanism in happening in a quantum spin liquid in frustrated spin system. So I think this is going to be a good topic in a workshop of this kind. So that deal with both fractional quantum Hall system and the quantum spin liquid or topological phases in quantum spin systems. So, okay, so what is coupled wire construction? I'm sure coupled wire construction is popular, but I'm sure it's not everyone's what everyone knows. So, so what is coupled wire construction? It is an interesting way of generating or constructing two-dimensional or three-dimensional topological phases starting from the one-dimensional quantum wires. So, and depending on the inter-wire interaction, which is designed for topological phases, some topological phases or ordered phases, we have a variety of phases. Some of them are ordered phases, conventional ordered phases like superconductivity or charge density wave, but sometimes we get highly non-trivial topological phases. That includes both symmetry protected one and long-range entangled ones. Okay, so I think this business has started from the coupled wire construction for fractional quantum Hall phases. Both include integer one and the fractional one. And so in this case, we start from the array of spinless fermion subject to an external magnetic field B. And depending on the value of magnetic field B, several special tunneling processes are allowed. And depending on these special tunneling processes, we can gap out bulk, but leaving non-trivial chiral Rattinger liquid on the edge of the system. So this is the idea of coupled wire construction. And also this strategy has been applied or generalized to a variety of systems, including a bosonic version of fractional quantum Hall systems, non-Abelian quantum Hall. And also it has been generalized to topological insulators and topological superconductors and fractional topological insulators and so on. Also, it has been generalized to three-dimensional topological ordered systems by including the more complicated interactions. Okay, so, but on the other hand, we know two-dimensional topological phases are not usually described by some kind of topological quantum field theories. So, but on the other hand, we know our starting point, coupled wires, are not at all topological. So the natural question to ask is that what is the mechanism of stabilizing highly non-trivial topological phases starting from this non-topological array of quantum wires? So this is a natural question to ask. And also, as I told you in the beginning of my talk, there is a at least formal similarity between gauge theory description of quantum spin liquid and emergent gauge field generation of the coupled wire construction. So this is going to be this is what I'm going to stress during my talk. So, okay, so here is the outline of my talk today. In the first part, I'm going to have some simple introduction. In the first part of the introduction, I'm going to give you a few simple examples of constructing the highly non-trivial topological state, starting from the simple degrees of freedom. And that will help you to understand the spirit of coupled wire construction. And in the second part, I'm going to give you a brief review or brief recapitulation about the relation between fractional quantum Hall effect and the Chern-Simons gauge theory description. And in the second section, I'm going to give you a brief review of the coupled wire construction and to explain how this this method works to construct two-dimensional topological phases. Also, in the third section, in the section 3, we start to calculate the number of inequivalent ground state starting from the coupled wire construction. Actually, normally in this coupled wire construction business, people just count the number of inequivalent ground state in a very naive way, but this is not necessarily correct. So I'm giving you a correct way of counting the topological degenerate ground state. That gives you a hint in identifying the gauge degrees, hidden gauge degrees of freedom in this problem. So in the fourth section, I'm going to derive the gauge. I'm going to identify the gauge degrees of freedom in the coupled wire systems, and derive the Chern-Simons gauge theory, which is topological, starting from coupled wire construction. This is the main part of my talk today. And then, using this strategy, I'm going to generalize the method to more general Abelian topological phases, which is characterized by K matrix. So in this section, I will solve a kind of inverse problem. So for a given Abelian topological phases characterized by K matrix, I construct and I will give you a coupled wire recipe corresponding to the topological phase. And the final section is going to be a summary and outlook. Okay, so let's get started. So first simple example of topological phase is the so-called Affleck-Kennedy-Lieb-Tasaki state of spin one chain, which is known to be a symmetrically protected topological phase. So this is a spin state in a spin one system. So physical degrees of freedom is clearly spin one object sitting on each side. But for at the first step, we divide this spin one object into two spin one halves. So we somehow expanded a physical Hilbert space, which is originally three-dimensional, to a four-dimensional object, which is spanned by two spin one halves, right? So then we combine these two guys sitting on the neighboring sides in this way. Namely, we put a maximally entangled pair on the neighboring spin one halves this way. So we can repeat the same game for this side and so on to make an entire non-magnetic state. So this is a cartoon picture of how we construct this kind of topological phases starting from spin one halves. So we have two spin one halves at each side, and we connect these two guys into a singlet, or maximally entangled state, to make an entire singlet state. Okay, so clearly by construction, this is a singlet in the bulk, but we have a spin one half, non-trivial spin one half edge state at the boundary. So if you calculate the spin density at each side, we get some emergence of the spin one half degree of freedom on one side and on the other side, like this. So this clearly illustrates the non-trivial nature of the state constructed this way. Okay.
Sorry.
Yes.
It looks like your curve goes above. Sorry, no, it goes above 1/2, but that's okay.
Yeah. Okay. So if you sum up all these spin density, we get the spin one half. Yeah. Okay. So similar strategy works for constructing the other lightly entangled state by using matrix product state construction. So we prepare some physical degrees of freedom and divide these degrees of freedom into two pieces, and then connect them into a singlet or maximally entangled pairs to make an entire state. So this is one way of constructing a topologically non-trivial state starting from simple physical degrees of freedom sitting at each side. Okay, so the second example is the so-called Kita-F chain of one-dimensional spinless P-wave superconductor. So this is my Hamiltonian. So we have a hopping term, and we have a pairing term, and also we have a chemical potential term. So this is a fermionic expression, but if you read, basically in principle, by using Jordan-Wigner transformation, we can rewrite this Hamiltonian by using a spin one half object. Then we get a so-called transverse Ising model, which is very well known in the history of quantum magnetism. So the key step is to rewrite these complex fermion by using in terms of the Majorana fermion in this way. So we have a complex combination of the two Majorana fermions, C1 and C2, to construct a single complex Dirac fermion this way. So in terms of these Majorana fermions, the Hamiltonian, my Hamiltonian can be written in this way. So we have an intersite pairing terms written here, which comes from the hopping term and a pairing term. Then we have an on-site pairing term, which comes from the chemical potential term. So graphically, this my Hamiltonian is written like this. So we have an on-site pairing term, which basically makes the trivial product state, on-site product state. And on the other hand, an intersite pairing tends to stabilize some non-trivial topological phase. Okay, so depending on the pattern of the pairing, we get several different phases. So this is a cartoon picture of illustrating how we construct a trivial phase. So if you pair Majorana fermion on each side, this way, on on-site way, we get a trivial phase. So this is nothing but a product state. On the other hand, if you pair Majorana fermions in this way, so we pair Majorana fermions on neighboring sites, you can gap out bulk, but then you can leave unpaired Majorana fermions. That's why we have a topological phase. So depending on how you pair Majorana fermions, we get either trivial phase or non-trivial topological phase with non-trivial edge modes. So actually, a similar strategy appears in the coupled wire construction to have a non-trivial edge state. Okay, so the third example illustrates you how we can extract a non-trivial gauge degrees of freedom starting from the system with obeying the local constraint. So to illustrate this, I'm going to take the example from quantum spin ice, which is realized in the spin 1/2 Ising like quantum antiferromagnet on the pyrocolor lattice. So this is a cartoon picture of the single tetrahedron, which is the building block of the pyrocolor lattice. So in building a pyrocolor lattice, we connect these tetrahedra in a corner sharing way like this. So this is a cartoon picture of a single tetrahedron. So local energetics of this Hamiltonian is given by this simple Hamiltonian. So you have 4 Ising spins, and sum all these guys on the 4 corners of the tetrahedra, and then you square these Ising spins this way. So clearly, so Ising spin up corresponds to outgoing spin direction, and the Ising spin -1 corresponds to incoming spin direction. So if you calculate the ground state energy of this simple local Hamiltonian, we can see the local ground state obeys a so-called local constraint, 2 in and 2 out. So namely, local ground state is characterized by 2 incoming spins and 2 outgoing spins. So this condition, local constraint, should be satisfied by all the tetrahedra. So all the constraints are not independent from each other. That's how we get a gauge field description. So clearly, this tetrahedra should satisfy 2 in 2 out constraint. But at the same time, these 4 guys must obey the similar constraint, 2 in 2 out constraint. So the spin description is not quite convenient in describing this highly degenerate ground state satisfying the local constraint 2 in 2 out. Actually, the best way of describing this degenerate ground state manifold is to introduce bond variables or gauge field variables like this. So if you have outgoing spins, we assign outgoing flux and so on. So this is how we get a gauge field description in highly degenerate ground state manifold, which is sometimes called ice manifold, because it's closely related to the degeneracy of water ice. Okay, so what about introducing quantum fluctuation to this highly degenerate ground state manifold? So if you carefully analyze non-trivial flipping processes which quantum fluctuation gives you, then we get this kind of flux flipping process. So this is a spin configuration along this tetrahedra, hexagon formed by 6 tetrahedra. So the first non-trivial quantum fluctuation gives you a flipping process of this gauge field configuration. So if you write down this process in terms of the gauge field, this is nothing but the cosine of curl A, so which gives you a B squared term in the quantum electrodynamics. That's how you get the non-trivial Maxwell electrodynamics defined on a diamond lattice, starting from the quantum spinors. Okay, so this is the idea. So by strong anisotropy, we somehow stabilize a highly degenerate, massively degenerate ground state manifold, which is called ice manifold. And if you include the quantum fluctuation within this ice manifold, we get a highly non-trivial emergent gauge field, which is nothing but the Maxwell electrodynamics on the diamond lattice. Okay, so we use a similar strategy in identifying the topological quantum field theory in this coupled wire construction. Okay, so.
Can you say a few words about the
yes?
The structure factor of the event?
Oh, yes. Okay, so if you, so this is a calculation of the result of the structure factor calculated for quantum spin ice. So you can clearly see some linearly dispersing mode at some special point of the K space, so which is nothing but a photon excitation in this system. So you can really see the photonic emergent photons in these quantumized systems. Okay, so I'm going to skip. So actually, this is my first serious quantum Hall talk that I ever gave. So if you have now I'm starting quantum Hall topics. So if you have any feedback, especially from the expert sitting here, I'll be very happy. So okay. So anyway, we already had about a good interaction with the quantum Hall effect yesterday from the Steve Simons talk. So I don't think it's necessary to give a detailed interaction. So what is quantum Hall effect? It's an exotic phenomenon realized happening in a two-dimensional electron gas in a high magnetic field. And as far as I know, this is the first example of a non-trivial topological state of matter. And also it's characterized by, so you measure Hall voltage shown here. So you inject a current in this way and measure Hall voltage, which is in a perpendicular direction to the direction of the current. So this is how you define Hall resistivity. And if you plot the Hall resistivity, you can clearly see some plateaus happening at the simple fraction of the filling fraction nu, which is defined here. So this is a quantum Hall effect. So I just give you a minimal interaction. So what is important here is that this phenomenon is normally has another description in terms of low energy effective field theory, which is known as Chern-Simons gauge theories. So the natural question is how this kind of non-trivial topological gauge theory appears starting from the strongly interacting electron system subject to the electromagnetic field. Okay, so there are several approaches in deriving Chern-Simons gauge field theory. So first one is based on the composite fermion or composite boson mean field theory. But I'm going to give you this one because this afternoon Yohei will talk about this approach. So I'm going to take a shortest cut in getting to Chern-Simons gauge theory. So this is the whole response. So this is what we should get in the end of the day. And also, we know the fractional quantum Hall state is an incompressible state of matter. So the theory, effective theory, at least low energy, long wavelength effective theory is written only in terms of the conserved current this way. So if you solve the conservation of the current, we can get this expression. So normally, namely, we can solve the conservation constraint by using the one-form gauge field here, A sub rho. So this is a possible form of the effective action. So this is a coupling of this conserved current to external electromagnetic field, and this is the main part of the effective theory, which is also a gauge theory, because if you write everything in terms of current, because current is a gauge invariant object, so this part should be a gauge invariant too. So we have a gauge theory here. Okay, so in 2 + 1 dimensional system with parity and time reversal symmetry broken, the lowest relevant, most relevant term which is allowed by gauge symmetry is like this. So this is nothing but a Chern-Simons gauge theory. So if you write this effective action in terms of current, this is nothing but a hop interaction between the currents, non-local hop interaction between currents. So if you formally integrate out this small mu gauge field, we get this effective action whole response. So if you take a derivative of this effective action with respect to large A, we get the whole response. So everything is fine. So what kind of physics coming out from the Chern-Simons, low energy Chern-Simons gauge theory? So this is my Chern-Simons gauge theory. So if you take an equation, clearly, first of all, this is topological. So if you take a derivative with respect to metric, this gives you zero Hamiltonian. So Hamiltonian 0. So you don't have any excited state. And also, if you take and calculate an equation of motion of this action, we get something like this. So this is the flux of the Chern-Simons gauge field, and this is quasi-particle density times 1 over m. So this means each quasi-particle carries 1 over m flux, Chern-Simons gauge flux. So this actually leads you to a non-trivial fractional statistics, which is given by the AB flux when AB flux each quasi-particle acquires when it encircles around the other particle. Okay, so basically this also gives you a Philip fraction, which is 1 over m, and also this term, which is gives you a charge of the quasi-particle, which is 1 over m. So also we can calculate the ground degeneracy starting from Chern-Simons effective action by calculating the commutator over commutation relation of the Wilson loops. So basically, this simple effective action already encodes most of the important information concerning the fractional quantum Hall effect. So this is nice. Okay, so let me quickly survey the how coupled wire construction works to constructing the topological fractional quantum Hall state. Okay, so in constructing fractional quantum Halls or Lafferin state, we prepare non-interacting spinless fermion wires subject to an external magnetic field B. So in taking a Landau gauge, the gauge potential will be given by this. So if you calculate a single particle excitation along each chain, it's going to be something like this. So we just shift the effect of the external magnetic field is just to shift the center of the dispersion in this way. So for the depending on the chair in question, we have a different center of the parabolic dispersion like this, right? Okay, so as usual, we take a low energy limit. So namely, we linearize the dispersion, parabolic dispersion around the Fermi points shown here. So this is right moving, and this is left moving, and so on. So we have a 2n gapless Dirac fermions at the starting point. Okay. So
Sorry?
yes.
You go back to this dispersion?
Yes.
So you are in the continuum?
Yes, continuum in the chain direction, but we discretize in the perpendicular direction.
I'm not sure I understand what you are.
Okay, so I took Landau gauge. So basically, the system is translation invariant in the x direction, but it's not in the perpendicular direction. And depending on the chain, we get some shift of the parabolic dispersion like this. So for the first chain, we get this, and for the second chain, we get this, and third chain this, and so on.
Okay, and you already included some hopping between the chains.
This includes the chain. So if you don't include, so we get a simple parabolic. Yeah, exactly. Yeah. Okay, so this is my starting point. So we get a Dirac fermion, chiral Dirac fermion, which are left moving and right moving, and plus some forward scattering, which is typically a density-density interaction, and plus other interactions, which are not written in the form of the density-density interaction. So now, next we bosonize this Dirac fermion to get this Tomonaga-Rattinger liquid form. of effective action. And we have two phase bosonic degrees of freedom, phi and theta, that describes low energy, low energy dynamics of the original fermion systems. So these two variables obey the standard canonical commutation relation. And also, they are periodic variables. So phi has a period 2 pi, and the theta has a period pi. And actually, this periodicity is very important in counting, in getting the correct number of degenerate ground states in the coupled wire construction. Okay, so then by using these bosonic variables, we get this expression for the right moving fermion and the left moving fermion. So now the next problem is to write the interwire interaction in terms of these bosonic variables. Okay, so now we have free fermion system. We start from fermion system and add some forward scattering plus some interwire coupling. So up to free fermion plus forward scattering, we get what we get is a so-called sliding Latinger liquid. So although we are dealing with two-dimensional systems, which is two-dimensional array of quantum wires, the system shows a one-dimensional behavior. This is a main point of the sliding Latinger liquid. So we have this topological Latinger and forward scattering and interwire. So now this interwire interaction, which is not written in terms of density-density interaction, gives you some instability from the sliding Latinger liquid fixed point. Okay, so basically, my interwire interaction is given by the polynomials of the fermion, right-moving fermion and the left-moving fermion. So in terms of bosonic language, it's given by the product of the vertex operators. So it's going to be something like this. So this is a generic form of the interwire interaction, my interaction. So this is this. So but then, so basically we have some integers, MP and NP, that characterize the form of the possible interwire interactions. So but then here are several selection rules coming from symmetry and underlying CFTs. So first of all, because each chain is described by bosonic or fermionic CFTs, and NP and NP should obey these selection rules. For instance, NP and NP should have the same parity for fermionic system, and NP should be even for bosonic systems. The second one comes from U1 symmetry. So if you shift the phi field in this way, this is nothing but a U1 symmetry, and require invariance under this symmetry, then we get this selection rule. So sum of MP should be 0. And also we can impose a translation invariance because we are dealing with continuum systems. So okay, so these two guys are coming from translation invariance. And actually, if you have a finite density, theta should be modified to this. And if you apply a magnetic field, the phi field should be modified by like this. And if you plug these two guys into this expression and requiring translation invariance, we get this non-trivial relation between the filling factor nu and the MP and NP. Okay, so now I'm going to illustrate how this strategy works to reproduce conventional ordered phases. So first one is CDW, charge density wave phase, which is stabilized by the interwire coupling, interwire interaction given by this combination. So n naught equal to 2 and n1 equal to -2. So in plugging these combination into my general expression, we get this. So this is nothing but a coupling of the CDWs on the neighboring chains. So this kind of interaction somehow stabilize in phase or out of phase coupling of the charge density waves on the neighboring chains. That's how you stabilize a two-dimensional charge density wave. So this is a usual mechanism of CDW stabilization. And the second one is pair hopping process, which is given by this combination. And if we plug this into the general expression, we get this. So this is nothing but a pair hopping processes. So we have a right mover here and right mover here, and then we have a hopping from right mover here to the right mover on the second neighboring chain. The same for the left mover here. So this is a pair hopping So if you have this pair hopping, you can stabilize two-dimensional superconducting order. So this is the example from the conventional phases. So what about, yes?
Can you come back maybe to the first picture when you linearize the...
Last slide?
So a couple slides before when you linearize the spectrum?
Yes, this one?
Yeah, so you start with decoupled wires.
Sure.
Then you linearize.
Yep.
So that means the perturbation has to be super weak because you have to stay in that regime, basically, if your energy...
Yeah, that my Baire coupling should be small.
So it's a perturbative...
Exactly. But
if the phase really is changing, you're not in the perturbative regime anymore.
yeah, but in the course of the renormalization group procedure, you can increase the coupling, the value of coupling constant. So eventually,
Outside of the circles.
sorry?
I mean, the bosonization is going to be not valid anymore if you really put a...
Exactly, yeah, sure.
So the whole approach is maybe down. You can't linearize and then put a strong perturbation.
Yeah.
Then your linearizer is not.
Yes.
You can only put a super small perturbation. And if things are flowing upwards, then the approach is the approximation.
Yeah, okay, I agree. There is some limitation within which we can safely apply bosonization approach. But then within a renormalization group approach, you can change your Baire coupling constant, which is weak in the beginning, right? If the interwire interaction is relevant, it's going to grow up to some maximum value which is allowed for this kind of low energy approach. Am I answering to your question? Okay, chat later. Okay. Okay, so yeah, so this is fine. This is fine. So what about integer quantum flow? So in stabilizing integer quantum flow, we introduce other one single particle hopping. So in the standard single particle hopping, we have a hopping between left movers and right movers. So we have both single particle hopping. But here we introduce very strange single particle hopping. Namely, we have a single particle hopping only between right mover and left mover here, and same for here. But we don't have a single particle hopping between this left mover and this right mover. So this is very special. So, so the point of this single particle hopping is that if you make a change of variables in this way, we can leave unpaired mode. So we couple these mode and these mode and these mode and so on. Then this single particle hopping will gap out the entire system, leaving an unpaired right-moving Dirac fermion at the edge of the system. So this is quite similar to what we did for Kitaev chain or AKLT chain. So if you introduce a non-trivial coupling between some fractional degrees of freedom, we can stabilize very non-trivial phase with an unpaired edge mode. So this is the idea. So what about a fractional case? So you can play the similar game for a Laughlin state. So now we introduce this interwire interaction. So we, in the previous example, m equal to 1, but here we have a non-trivial m here. So this corresponds to a choice of MP and NP here. And if you plug everything into the formula of the fitting fraction, we get 1 over m. So this should describe the Laughlin state. And the trick is to we make a change of variable shown here. So we move from the original fermion basis to a quasi-particle basis defined here. So if in terms of this quasi-particle basis, my interwire interaction takes the form of the backscattering. So we can take the same steps as before for integer quantum Fourier effect to gap out everything in the bulk in this way. But we again leave the non-trivial edge state, which is not paired in the bulk. So this is how you stabilize the non-trivial chiral edge state in the Laughlin state, starting from coupled wire construction. Okay, so this is the idea. Okay, so now I hope now you understood the spirit of coupled wire construction. So here are several issues. Clearly, bulk effect, we already know bulk effective series are known to be a Chern-Simons gauge theory. And clearly, the idea of Topmat liquid is not at all topological. So the natural question is how non-trivial bulk topological state emerges from the coupling of the coupled array of the wires. So okay, normally in the business of coupled wire construction, people only talk about non-trivial edge state. That is a kind of signature of the non-trivial bulk. But then non-trivial edge state emerges from the non-trivial bulk, right? So I think the best way of demonstrating coupled wire construction, really constructing a non-trivial topological state, is to show the non-trivial bulk topological gauge theory emerges from the coupling of wires. So we have now two non-trivial questions. So the first one is how non-trivial bulk topological gauge theory emerges in the interwire couplings. And also, is it possible to find the coupled wire list for any given two-dimensional Abelian topological phases? Okay, these are two questions. Okay, so let me count. Before identifying the gauge degrees of freedom in a coupled wire construction, let me count the number of inequivalent ground state starting from within the framework of coupled wire construction. So this is my interwire coupling. So this theta field is a kind of bosonic field obtained after change of variables. So this is nothing but a backscattering of some quasi-particles. Okay, so according to the standard recipe of bosonization, if you have a very strong cosine interaction here, we can somehow pin the value of theta around theta here. So we get we have some minimum of theta equals 0, plus minus pi, and plus minus 2 pi, and so on. The same game is you can do the same game for each chain. So we have, so for instance, you have theta pinned here for the j minus 1 chain, and for the jth chain, theta is locked to here, and for the next chain we have something here, so like this. So you may think we have an infinitely many ground state in the strong coupling limit of the coupled wire system. But this is not quite actually true, because so this is a definition of the round theta field, and the theta field is made up of two mutually dual fields, namely phi and theta are dual to each other. So you cannot simultaneously pin these two fields. This is a key point. And actually, if you shift round theta by pi, this is absorbed by a shift of another another chain by pi. And actually, these two processes are equivalent to each other by the periodicity of the phi field. So you need to take into account the periodicity of the bosonic field like this. Okay, so what is the periodicity of the or gauge redundancy of the bosonic field? Because my chiral fermions are written in terms of these in terms of the chiral bosonic field like this. So these chiral bosonic field phi sub L over R should have a periodicity of pi. And if you have a bosonic field, phi should have a periodicity of 2 pi, and theta should have a periodicity of pi. So we need to take into account this periodicity in correctly count the number of the ground state. Okay, so actually, looking at the definition of the phi and on-wire variables, phi and theta, it's made up of two contributions. So theta, we already know by the interwire interaction, we somehow stabilize, pin the round theta variables. So we can, these guys take that finite expectation value. But on the other hand, round phi, which is dual to theta field, are strongly fluctuating. So you cannot pin the phi field on wire variables phi and theta here. So this is a point. Okay? But there is one way of killing these fluctuation pieces. Namely, if you take the sum of theta field, you can suppress these fluctuating pieces. So that's how we define the Wilson line, which is going to be a useful order parameter in identifying the ground state, right? Okay, so now we are at the place of counting the getting the correct number of ground state. So, okay, so this is the periodicity of the bosonic variables. So now we ask, now we take two ground states defined by delta around theta. So we have a ground state 1 and ground state 2. And the theta values for ground state 1 and ground state 2 are different by this delta around theta. Then we ask if this difference is absorbed in the periodicity shown here or not. So this is the question. And if the difference delta around theta is absorbed in this periodicity, the two ground states are actually gauge equivalent to each other, so they are the same. But if you cannot, these two ground states are physically equivalent, non-equivalent. Okay, so the answer is very simple. So actually, the calculation is very interesting, but it's a bit lengthy and complicated. So if you are interested, please ask later. So this is the answer. So okay, two ground states that differ by this delta around theta, which sums up to M0 modulo M pi, are actually gauge equivalent to each other. And the converse is also true, right? So this gives you a criterion for the counting the correct ground states. So, okay, so if you look at the definition of the Wilson loop that I defined in the previous slide, we can immediately see we have M different ground state distinguished by the eigenvalue of this Wy, Wilson loop Wy. So we can see the same result. We can get the same results from the slightly different viewpoint. Okay, namely, we can consider quasi-particle transport, which is written in this way in terms of the bosons. So this is the expression of the quasi-particle transport written in terms of the boson. Okay, so yes. And if you calculate the commutation relation of these two guys, we have some non-trivial phase. So if you act ukx, k's power of ux, we have some different different ground state starting from some reference state. So this is my state, and if you calculate the eigenvalue of uy, we get this. So this is an eigenvalue of this is reference state with respect to this uy. So we have a shift of minus k pi if you act ux to the k. So this means if you repeatedly act on a ux operator, transpose operator, you get a different ground state measured by this Wilson quasi-particle transport. And actually, if you repeat this m times by this gauge equivalency, we get a starting point. So this is how we have an m degenerate ground state. Okay, so now we are ready to identify the gauge degrees of freedom. So in the absence of interwire interaction, we have a sliding Latinger liquid. So the system is invariant and under some shift of the chiral degrees of freedom, phi L and phi R. So these two guys are independent from each other. So we can do the same game for all the chains. So we have, in total, 2n independent degrees of freedom, continuous transformation. But in the strong coupling limit, we cannot do this. We cannot change these two guys independently. Actually, so this is the starting point. We have 2 degrees of freedom, and zeta L and zeta R on each chain. But in the strong coupling limit, somehow these two guys are strongly coupled to each other, right? So actually, in the strong coupling limit, these two guys must go in hand. So we have the same value for this and this. But still, we have some residual continuous U1 degrees of freedom that does not change the strong coupling ground state. So this is the key in identifying the gauge degrees of freedom. Okay, right. So if you plug this transformation, you can really see around phi transforms like a standard matter field, and the theta around theta is invariant as required. Okay, so this immediately gives the identification of the bosonic field with some gauge degrees of freedom. So X component of the Chern-Simons gauge field is identified with a derivative of phi, round phi, and Y component is identified with theta, on Y variable theta, right? So if you are familiar with Chern-Simons gauge field, this identification correctly reproduces a standard decoupling of the Chern-Simons gauge field into two pieces, namely a gradient part, which is periodic, and the holonomy part, which is not periodic. So clearly, this phi part gives you a gradient part, which is pretty periodic, and this round theta part gives you a holonomy part of the gauge field. Okay, so now that we have identified the gauge degrees of freedom, we are at the place of rewriting the coupled via Hamiltonian or coupled via action to the Chern-Simons action, right? So okay, in the strong coupling, so now let's suppose we are deep in a strong coupling limit. Then, so this is my Hamiltonian, and this is a sliding Latin liquid part, and we have some interwire interaction, which is written in terms of cosine-like interaction. But deep in the strong coupling limit, normally K diverges, so we can forget about this term. And this is my strong interaction, which gives you an ice manifold of this problem. So because we can forget about this term, actually, only the Bailey phase term shown here survives in the deep in the strong coupling limit. So all we have to do is to plug this identification or this formula into the Bailey phase term. So if you do that, we get this form. And actually, this is nothing but a Chern-Simons gauge theory within a wide gauge. So this is Chern-Simons action. And if you take a wide gauge, you can forget about this term. And this is nothing but what we get here, right? So somehow we can reproduce Chern-Simons gauge theory starting from the coupled wire construction in the strong coupling limit. Okay, so we can check several formulas known for Chern-Simons gauge theory approach. For instance, you can reproduce a density operator. You can rewrite the density operators in terms of Chern-Simons flux. So this is fine. And also we can define a Wilson loop starting from the bosonic description, and which obeys the correct computation relation. Okay, so this is everything is fine. So far, so good. Okay, so maybe I'm going to skip this. So this cartoon picture summarizes what we did for in deriving the Chern-Simons gauge theory, starting from coupled wire construction. So if you take the strong coupling limit of the interwire interaction, somehow we are restricted yourselves to an ice manifold or degenerate some restricted ground state manifold, which has an emergent gauge degrees of freedom. Actually, this is not a gauge symmetry. This is kind of gauge redundancy, because we already know we have only M degenerate ground state. So this continuous degeneracy is a kind of redundancy in the description. So now we have only within this degenerate ground state ice manifold, we have some emergent gauge degrees of freedom. And if you correctly identify the gauge degrees of freedom in terms of bosons, and we get a Chern-Simons gauge theory. This is what we did. And actually, we have an infinitely higher lying excited state shown here in the strong coupling limit. And this part is not two-dimensional, actually. This is strongly one-dimensional. So the ground state manifold is highly two-dimensional, but then excited state is very, very one-dimensional. So this is coupled wire construction is a way to construct a topological part of the system. But it's very different, including if you take into account the excited state as well, it's very different from the two-dimensional electron gas in the magnetic field. So this is, okay, this is a split, but I think the time is running out. So I'm quickly go through my second part. So now we know the strategy of getting the Chern-Simons or topological quantum field theory in the bulk. So the next question to ask is it possible to apply the similar procedure to write down the coupled wire recipe for given general Abelian quantum Hall systems? So it is known that general Abelian topological phases, in two-dimensional topological phases, can be written at least in the low energy limit by this multi-component Chern-Simons gauge theory characterized by this K matrix. And so we have a K matrix, which is a symmetric n by n symmetric matrix with integer components. Then we have a coupling to external magnetic field shown here. Then we have some integer number q, which is called charge vector here. On a K matrix and charge vector and L, which characterize excited quasi-particle excitation, gives you a fundamental data of the topological phases. Okay, so I'm going to skip this maybe. Okay, we can, within this framework of Chern-Simons theory, we can get the topological ground state degeneracy, which is given by the absolute value of determinant K. And also we can give a free inflection in terms of K matrix and a charge vector Q. And the whole response is shown, given by this, and so on. So everything is fine. So now, let me ask, is it possible to find a quantum coupled via construction for this K matrix Chern-Simons gauge theory? The answer is yes. Actually, the result is very simple. So we just replace the integer m for our Laflin state by a K matrix here. So, following the similar procedure as before, we can identify the gauge degrees of freedom, so which is given by this formula. So x component of Chern-Simons gauge field is given by this in terms of the boson phi, and y component is again given by the theta component of the bosonic field, right? So again, in the strong coupling limit, we can forget about the sliding Latinger liquid part, and we get only the Bailey phase term. And if you plug these formula into the Bailey phase term, we get the Chern-Simons action in the Weyl gauge again. So now everything is fine. So, but we know there are several basis choices for K matrix formalism of the Chern-Simons gauge theory. So the next question to ask is which basis? Actually, we can find the basis by this reasoning. So specifically, I start from some quasi-particle creation operator, which is given by this in terms of boson. So if you calculate the charge created by this quasi-particle excitation, we get this result. So basically, this is given by the inverse of K matrix. So if you equate this result with the general expression of the Chern-Simons gauge theory, we see Q, charge vector Q, is given by 1, 1, 1, 1. So namely, the coupled via construction we found is corresponding to Chern-Simons gauge theory in a symmetric basis. Okay, so yes, so you may ask, is it possible to find some coupled via construction for corresponding to hierarchical construction of the fractional quantum Hall system? For the moment, we couldn't find the right answer for the hierarchical construction for some reasons, but so unfortunately, this is not successful description. So normally, in the coupled via scheme, we find Chern-Simons gauge theory in the symmetric basis. Okay, so okay, let me finish soon. Okay, so basically, my strategy of constructing a general Abelian topological phase characterized by n by n K matrix is to prepare n layers of coupled wires and connect them by some designed interaction, which is given by cosine interaction. But you can rewrite this system on a single layer problem by introducing a further range hopping processes like this. So namely, you just crush the n layer system in a single layer. So oops. Okay, this is an illustration for a double layer system. So we have a first layer here by red wires, the second layer here shown by blue wires. And if you crush this bilayer system into a single layer, we get this. So we have a first chain, we have a contribution from the first layer, and in the second chain, we have a contribution from the second layer, and so on. So we have some period 4 interaction, and so on. So that's how you rewrite the double multi-layer description in terms by a single layer description. Okay, so I'm going to skip. So this is. So you can play this game for. Okay, so you can. So this is how this illustrates. This slide illustrates how this strategy works for describing the Horden-Halpern hierarchy for nu equal 2/5, which is given by the K matrix in the symmetry basis shown here, 3, 2, 2, 3. And following my procedure, the inter-wire interaction that will stabilize this topological phase is given by this. But you can make a change of basis to reduce the number of interaction this way. And if you crush this bilayer system into a single layer system, we get this inter-wire interaction in a single layer system. So actually, this inter-wire interaction is already given by Taylor and Kane by some heuristic argument which I couldn't follow. But anyway, I can report this a known result. So this is a summary of my talk today. So okay, I explained to you how I can identify the gauge degrees of freedom in a coupled wire system and reproduce the topological quantum field theory starting from coupled wire construction. And also, I generalize my strategy to describe generic Abelian topological phases. And basically, this strategy is based on the multi-layer construction of the topological phases. And also, we can describe the VS theory in a similar way. And all these stuff correspond to a Chern-Simons gauge theory in a symmetric basis. So what remains to do is to find a similar gauge field description for non-Abelian fractional quantum Hall effect. So we already know some coupled wire recipe for Moore-Reed state or Reed-Rezer state and so on. So my next question is to find a similar gauge field identification for these coupled wire recipes. And also it would be interesting to consider synchronous limit that can relate your topological, highly non-trivial topological phase to a more conventional phases. Also, it's going to be very interesting to think about the three-dimensional cases. I think I will stop here, so thank you for your attention. In terms of, for instance, fermion, original fermion, or
yes.
Mm-hmm.
I think it doesn't matter.
Yeah.
What those?
For Lafferty, okay. So let me. For Lafferty state, we can do. It's very simple. So where is it? No, not this. Yes, yes, it's here actually. So this is not the one. Okay, so we have some cosine of phi minus phi plus m times theta plus theta or something. But you can rewrite this cosine interwire interaction in terms of the original fermion, which is shown here. So we have single particle hopping between these wires. But on top of this, we have some backscattering, on-wire backscattering interaction, so which is given by m minus 1/2 particle backscattering. So in principle, you can write down everything in terms of original fermion. But typically, which is in multi-particle processes.
Even one step further, if you have lattice.
Mm-hmm. And?
This step that you say that we can write it using the fermionic framework.
Yeah, sure.
After say we linearize.
Yeah.
We linearize on the parameter.
Mm-hmm.
But there is, let's say we start with some Hubbard-like model or whatever. These and other. So are you saying that we are able to control the ground state by instinctively choosing?
Yeah, actually that's a tough question. So we just assume we can stabilize, or you can make this interval interaction most relevant among all the possible interactions. This is my assumption. Actually, Teo and Kane gave some hand-waving argument for simplest cases, but I don't think it's easy to find a general argument for generic cases.